Okay, physics students, we are going to talk about the momentum principle. This is the next standard. I'm going to give a quick overview of it. Let me just say one quick thing about the momentum principle. Here I have a ball, and if I let go of that ball, it falls, and I got to pick it up. So in the beginning, people said, what's going on with that falling ball? And there was a great guy, and his name was Aristotle, and Aristotle says, well, the ball's falling, so something makes it fall, and if you push on something like the ball, or if you push on it sideways, this is a better example. Actually, if you push on it sideways with a constant force, it's going to move at a constant speed. The harder you push, the faster it goes. And that all made sense. And everyone said, yes, Aristotle's so cool. And Aristotle was wrong. And it turns out that forces don't make things move. Forces change the motion. And change is the key word there. And that's where we get to the momentum principle. What do forces do when the net force is not zero? We've already looked at what happens when the net force is zero vector. But now what happens when it's not? So the first thing we need to consider is the idea of momentum. So we can define momentum. Momentum is the product of mass and velocity. And velocity is a vector, and mass is a scalar. So when you multiply those together, you get a vector. So momentum is a vector. And this is what changes when you exert a force, a net force on something. So let me just go ahead and write out the momentum principle, and then we can talk about how it works. F net delta P over delta T. That's the momentum principle. It says that a net force changes the momentum with respect to time. It's very useful. It's very powerful. So let's just look at a quick example. Let's say I have this ball. And actually, to make it not completely trivial, this ball is moving along at 1 meter per second, and I push on it. It's moving this way, but I push this way for 1 second. Everything's 1, okay? Except for the mass of the ball. It's 0.1, 100 grams. Okay, so here I have the ball, P1, and then I push on it this way. This is my only force acting on it, F net. And then so what's going to happen is the ball is going to be going like that, P2. And I want to find that final momentum vector. So let's just use the momentum principle and solve this for P2. So I'm going to say equals P2 minus P1 over delta T. That's the same thing as change momentum. I can multiply both sides of this equation by delta T, and I get F net delta T equals P2 minus P1. Yes, these are vectors, don't forget. Now I can add P1 to both sides, and I get the following. P2, P1 plus F net delta T. So now I can find P1, I can find F net. These are all given. I can use that to find P2. So let's just pick some values here. Let's say the mass is 0.1 kilograms. V1 is 100 meters per second. F net equals 010 newtons. And delta T equals 1 second. So now I can just put in my values here, and I get P2 equals P1. P1 is going to be equal to mass times velocity, so that's going to be 0.1 times 1 is 1. The units for momentum are in kilogram meters per second. And yeah, there are no special units for that other than that. I know it's weird. But. Okay, so P1 is going to be equal to 0.100 kilogram meters per second. And then F net times dt is going to be 1 times 0, 1 times 1, 1 times 0. So it's going to be, but you'll notice here I get Newton seconds. And a Newton is a kilogram meter per second squared, so Newton seconds is a kilogram meter per second. Same units. So I get plus 010 vector kilogram meters per second. Now I can add these two. I get 0.1 plus 0 is, yeah, I know, it's easy. Okay, it's 0.1. So it's going to be 0.1 0 plus 1 is 1, 0. Kilogram meters per second. So that's my final momentum. Now what if I wanted to find the final velocity? Then I'd have to divide by the mass. So if I divide this by the mass of 0.1, I get 1, and then that's going to be, what, 10? Is that right? 10? Yeah, 10, 0. I won't write it out because I'm running out of room. But that's your basic introduction to the momentum principle. Okay, now some other important things. Some people may say, hey, but what about Newton's second law, right? What about that? Same thing. Okay, I'm going to show you, for the most part, it's the same thing. It's not completely the same thing, but for the most part it is. Okay, let's say, I'm going to erase this and start over. But you did notice two things in that problem I just erased. One, it changed directions. You can do that. Two, it actually changed magnitude too, because it didn't change the magnitude of the speed in the x direction, but it did in the y direction, so the total was different. Okay. These are vectors, that's important to realize. And this is the net force. Okay, I'm going to put in my definition of change for momentum here and say delta mv over delta t. Now, in the special cases where the mass doesn't change, I can factor that mass out of the change and I get m delta v over delta t. And we remember from before that the definition of average acceleration was a change in velocity with respect to time. So this is ma. Okay, so that's Newton's second law. It says F net equals ma. It's essentially the same thing, except that it's not. There are cases, and we'll use this sometimes because it makes things easier, but this is actually more fundamental because this includes cases where the mass is not constant. This includes cases where the definition of momentum doesn't work, and in fact, if you go really, 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 really fast, like rocket, spaceship fast, then there's a better definition for momentum, and this works. This doesn't work. Okay, anything else about momentum? That's super quick. But once we find the change in momentum, we can find the change in velocity, we can find a whole bunch of other things. Let me say one more thing, because I already wrote it down. The momentum update formula, I already solved for this, but here, remember this? P2, P1, plus F net, delta t. That looks a lot like the position, the velocity update formula. Let me do that. Actually, yeah, wait. That is the velocity update formula. That's the same thing as the velocity update formula if the force changes. And then we could use that with the position update formula plus the velocity, which is going to be actually P2 over m delta t. And then T2 equals T1 plus dt delta t. So this is what we use in our numerical calculations. If the force, and this actually doesn't even matter if the force is constant or not. Okay, so we're going to do that. We did it before using acceleration. It's the same thing. It's just a different way of viewing that picture. Okay, that's enough for the momentum principle for now because it's over 8 minutes and that's a little too long for me.